In the last video, we discussed the first law of thermodynamics and thermal processes. And the last process we discussed was the cyclic process. The cyclic process is a very interesting process because the system ends back at its initial state. That means it has the same temperature it had when it started, the same particle number, the same volume, the same pressure, and any other variables that define the state. This means that we can do this process over and over and over and over again. This leads to what is called an engine. An engine is a cyclic device which transfers energy as work. Now, it can transfer any type of energy out as work, but an important type that we're discussing here is the heat engine, which absorbs heat from the environment into the system and converts that to work that it then does out to the environment. So it's a converter. It gets the heat in from the environment and converts some of it. We'll find out it can never convert all of it into useful work. You can also reverse that process and in fact take work be done by the environment to cause it to transfer heat out of the system. When you do this, you get what's called an refrigeration system. So in our diagram of cyclic thing, we know by the first law that delta U is equal to Q minus W. But we know for cyclic systems there is no change in the internal energy. Therefore, Q is equal to work. And you might say this is the net. So this is work by system. And this is heat absorbed. Now, it turns out that it may absorb more heat at some points and then give some of that heat off, and it will, in fact. We'll look at that when we get to dealing with efficiencies of the engine. So we're converting heat energy to work. Consider the heat engine below. I'm going to draw a hot temperature area that can supply heat. And so Q, which I'll call QH, some amount of energy, can flow into my system from this hot source. That hot source could be a boiler where I've thrown coal in to burn. It could be nuclear power where I've heated water, and that's given energy because it's made it hot. Some of that work will go out of the environment. It would be nice if all of it did, but it turns out you cannot make a cyclic process and close the loop and get it back to its original temperature if you don't also expel some heat to a lower temperature reservoir. So let's say we take in 10 joules here, maybe 6 joules goes there, 4 joules come out as work. So when I say Q net, what I mean by that is that this Q net is going to be the difference between the amount of heat that we bring in and the amount of heat that we take out. Now, heat engines come in many different shapes and sizes and many different processes. So I'm going to try one here, just nothing special about it. But in this process, we're going to start at state A, and we're going to follow an isothermal process, which means we're going to stay constant temperature and hence also constant internal energy. And we're going to go to some new step, step B. So on this process, we keep a constant temperature, but we see there's area under the curve right here. We could maybe, for instance, draw that for the moment as like red area here. So work was done in this situation, but there was no change in the internal energy. That means that in order for that work to occur, there had to be heat provided by the environment. The heat that was provided was our friend QH. Now, after it gets to this point, I'm going to have it go and do a isovolumetric process down to some new state. This state here being state C. During this step, there is no work done, but I'm going down to a lower temperature. I know that because these isotherms go up in temperature, they go higher in pressure. When you heat a gas, you raise its pressure, and I'm lowering its pressure. And the way I can do that, as I showed earlier, was for a constant volume, I just stick some ice cubes or something on it and cool it. So I change that to a lower temperature, and now I go and I take another isothermal process back up to a new point, point D. Point D. And during that process, I'm going the opposite way, so I'm doing negative work. So I'm doing this much negative work. And so what that does is cancels out. And so the net work that's being done over the whole process is this area bounded in here. That's W. Now, I'm not back yet to my original temperature. I haven't gotten back to step A. So I need to follow one more process. This time I stay the same volume, but I heat the gas, moving it back to point A. Now, I can do any process. I don't have to heat it, but I do something that moves it back up to step A. It turns out that the energy to change internal energy here with no work is exactly equal and opposite about what it takes to do here. These two cancel. But what is different is that because I was at a higher temperature, I absorbed more heat, QH, than I lost heat by expelling it here, which was QC. And the difference between those two is the area bounded by this curve, which is W. So I've converted a fraction of the heat that I initially absorbed into work, and the rest I passed back out of the system. So it was not 100% efficient. It didn't convert 100% of the initial heat QH into work. It only converted a portion. This is always true. Some of the energy is lost in the random motion of molecules in the exhaust out of your car or in the water that gets discharged from a nuclear power plant back into the lake. And that energy you don't get back. Only a fraction gets done. So, in all of this stuff, let me put some things down. From A to B, that was QH. And then going from C to D, that was QL. And that the bounded shaded area gives us the work. And the work is equal to QH minus QL, which I called earlier Q net. The efficiency of an engine, by definition, is the work that it produces divided by QH. Of all the energy it pulled in at the hot temperature cycle, some of it passed on and just shipped it out, but some of it was converted into useful work. So the amount that you converted out of the total amount that you absorbed is what we call the efficiency. And it's always less than 100%. Now, the work, we already said, is QH minus QL over QH. You also, of course, could write this as 1 minus QL over QH. You'll never find that any system is 100% efficient. And the reason is you always have to have a path back to get back to your original start. And when you go back this path to get back to where you started, whether it looks like this diagram, it looks like this diagram, whatever diagram it looks like, you're going to have heat change. You're going to lose heat. So for instance, in this case here, if we'd have done this one, this would have been the cycle in which QH was brought in, but there would have been a QL here, and that QL would be negative. All right, so it would be heat out. In fact, we generally draw it like this, which is why I put a minus. If you draw the arrow going in, you have to add them. You have to say it's QH plus QL, and then the QL value would be negative. But we usually say we know it's going out and we draw the arrow going out. All right, it is easier most of the time for us not to work in terms of heat energy that we moved, but to work in terms of temperatures, the difference between the isotherm at the top here and the isotherm at the bottom. In other words, how hot was the fire? How cold was the exhaust or the water? To do this conversion from this to heat requires another concept, the concept of entropy and the second law, which we'll talk about in the next video.